Good morning, everybody. Welcome back to campus, folks, and the start of a new semester. Glad to have you back. What brings us together this morning is the Meyer Birnboim Rheology lecture. And this is a lectureship that has been established in memory of Professor Meyer Birnboim. I'll have a few words about the lectureship, and then we have a member of the family, Professor Birnboim's brother from Toronto, will be dialing in to make a few more comments about his brother's legacy and the lectureship series. And then I'll introduce our speaker, Nitash Balsara. So a little bit of background on Professor Birnboim. He was born in Poland and moved to Canada as a child. His academic training was all in various portions of physics, bachelor's and master's studies in physics at the University of British Columbia, followed by a PhD at the University of Wisconsin. So following his academic preparation, Professor Birnboim was a fellow at the Mellon Institute in Pittsburgh. And I happen to have in some of the random records at RPI, the CV that Professor Birnboim submitted when he applied for his professorship here, which is very interesting. And I saw that he had published several papers with a number of faculty members at the Mellon Institute who I ran across in a prior academic life. So the degrees of separation are very narrow here. Following his stint in Pittsburgh at the Mellon Institute, he became a professor at Rensselaer Polytechnic Institute. And at the time, the institute was organized into clusters, and he was part of the thermal fluids group or cluster, and that was led by Professor Coonley of chemical engineering, for whom the Coonley Lounge is named. And so that established a close connection between Professor Birnboim and chemical engineering at the time. His research interests covered instrument development and especially optical instrument development in order to characterize different materials, including biomaterials and inorganic materials. And he had extensive collaborations on campus, as most faculty do, and those collaborations centered in the physics department and in chemical engineering. And one of the later collaborations that Professor Birnboim had was with Joel Plowski, our prior department head. So at that time, Joel was just starting out, I believe, as a faculty member, having come from Corning Glass, very interested in ceramic materials, and Professor Birnboim had similar interests in all sorts of very interesting optical tools for characterizing these materials. And I have a picture here of Professor Birnboim hard at work, and just a small collage of a number of papers from later on in his career at RPI that he produced with Joel as a co-author. So the lectureship was endowed in 2022 by the Birnboim family, for whom we're very grateful. This is an alternating series that promotes interactions between engineers and scientists in the two foci of Professor Birnboim's career, and that was in rheology of materials and optical techniques for characterizing materials. This is the third lecture in the series, the second rheology-based lecture. The first was in 2022 with Norm Wagner from the University of Delaware. The second was in optics that was hosted by the physics department with Julie Bettine of the University of Michigan. And now we're delighted to have Professor Nitash Balsara return to campus from UC Berkeley. I want to very clearly thank the Birnboim family for honoring the memory of their family member, Professor Birnboim, and the contributions he made to science and engineering, and also for honoring the chemical and biological engineering department and the physics department by supporting this lectureship series in Professor Birnboim's memory. So thank you for that. I'd like to introduce at this point Professor Birnboim's brother, Dr. Chaim Birnboim, who is dialing in from Toronto, and he will provide a brief introduction to Professor Birnboim's background, and the genesis of the lectureship series from the family's perspective. So Professor Birnboim, if you're online, or Dr. Birnboim, if you're online, the floor is yours.
Well, thank you very much. If I can I be heard?
Yes.
Yeah. Good. Okay. So first, I'm pleased that there were some details of my brother's background, academic background that I didn't know. Our younger brother, and we parted ways early. He was older than me, and he went on to science. I want to welcome to all who are in the auditorium and the viewing audience for attending this lecture by Professor Nitash Balsara. As we just heard, this lecture is part of an annual series established by the Birnboim family to honor the memory of Meyer Birnboim, professor in the Mechanical Engineering Physics Department at RPI from the late 60s until his passing in 1996. I am Dr. Chaim Birnboim, my younger brother of Meyer Birnboim. Intending in person this year, I think, I haven't communicated with him, is Meyer's widow, Alma Birnboim from New York City, his son, Yosef from West Orange, New Jersey, and a nephew, Jason Birnboim from Toronto, Canada. Roy and I, Meyer's two younger brothers, live in Toronto and regretfully are unable to attend in person because of health reasons. Other family members live in New York, Toronto, Winnipeg, and elsewhere, and hopefully will be viewing a recorded version of this video of this lecture. Now, in addition to being a much beloved husband, father, grandfather, and brother, Meyer Birnboim's chosen professional career, as we've heard, is in science and technology. And I have some details, but we just heard some about his background. I forgot about his bachelor's degree, but he had obtained a master's degree in physics at the University of British Columbia in 1956, I believe, before pursuing, here's some more detail for you. Before pursuing a PhD, he worked for a year in Winnipeg and what was called the Grain Research Laboratory. As some of you may know, Canada is an important exporter of wheat and other cereal grain to many countries of the world. Meyer had a role in perfecting flour to make the perfect bread. He developed a rheological instrument to measure the viscoelastic properties of flour made from different strains of wheat. As a child, I remember his bringing home small loaves of perfectly baked bread, each with slightly different texture. He then went on to pursue a PhD in physics at the University of Wisconsin, but it was under the supervision of the father of the at least an early pioneer in the field of rheology, Professor John D. Ferry, who, by the way, was also Canadian. Meyer was also a visiting scientist at the Carnegie Mellon University in the lab of Guy Berry, at the Weizmann Institute of Science in Israel in the laboratory of Alex Silberberg. But as I say, his home institution was here at RPI, where he was a professor, I thought, in mechanical engineering and physics for nearly 30 years. My own background is actually in medicine. I'm a scientist in biochemistry and molecular biology. And it was from Meyer that I learned to recognize viscoelasticity was a readily observable property of double-stranded DNA. Regretfully, I never did get to see the Birnboim-Schrag multiple lumps resonator that bears his name. As to today's speaker, I do know a little bit about the movement of charged polymers such as DNA in neutral solvents, but nothing about Professor Balsara's work in improving battery efficiency through the use of neutral polymers as solvents. So I look forward to hearing today more about his rationale and his experimental results using this approach. We're grateful to the Isserman, members of the Isserman Department of Chemical and Biological Engineering for organizing this year's Birnboim Lecture in Rheology, and we look forward to hearing this year's talk by Professor Balsara. Thank you very much.
Thank you, Dr. Birnboim. And in some mark of the impact that the Birnboim family has had, Dr. Birnboim himself is the inventor of the alkaline extraction method for plasmid DNA from bacteria. So a fair number of people in this room have used that technique. So at this point, I'd like to turn our attention to our speaker, Professor Nitash Balsara. So Nitash did his preparation all in chemical engineering, starting off at IIT Kanpur, doing a master's a bit north of us at Clarkson University, and then joining RPI for his PhD studies, where he studied under Bruce Nauman and defended his PhD in 1988. So after defending his PhD, he went on to two different postdoctoral positions, one at the University of Minnesota, another at Exxon. And then he joined the faculty at Polytechnic University in New York City. And following a stint at Polytechnic University, moved ultimately to UC Berkeley, where he holds an appointment, faculty appointment, both in the chemical engineering department and also scientist appointments at the Lawrence Berkeley National Laboratory. And his current title is the Charles W. Tobias Professor in Electrochemistry. Professor Balsara's research interests are centered on electrochemical energy and ion transport, about which we'll hear more today, and in particular the design and synthesis of polymer electrolytes that support lithium batteries, safer lithium batteries, and also in materials characterization techniques that can be used to study these materials, including X-ray scattering techniques, tomographic techniques, neutron scattering, and cryo-electron microscopy. He's also a serial entrepreneur, having started two different companies, CO Incorporated and Blue Current, both working in the rechargeable battery space. The first working on rechargeable lithium-ion batteries with nanostructured polymer electrolytes. And then Blue Current working on batteries with a new type of chemistry based on silicons. He has been awarded numerous awards. I've got a selection of the awards he's received here, starting off with a Young Investigator Award from the National Science Foundation, the Dillon Medal from the American Physical Society, Dreyfus Foundation Teacher Scholar Award, and one that's near and dear to our hearts, the Hendrik Van Ness Lectureship at RPI in 1998, and more recently, the Stein Award from the AICHE Materials Engineering and Science Division. It's my pleasure to welcome to the podium Professor Nitash Balsara. And if you'll come forward, Nitash, we have a plaque for you. All the photographers done their thing? Okay.
Pick up photography.
All right. The photographer of last word. The floor is yours.
It's an unbelievable honor to be here and face all you folks. While on the subject of Birnboim, Professor Birnboim, I took his class in polymer physics. I would argue that it was the only polymer physics class I took while I was at RPI. I was introduced to polymers by Bruce Nauman, and it's a field that I never left. And I took every polymer class there was on campus, but the most memorable lecture was by Birnboim. He began this lecture by telling us about Peter Debye and how he figured out what the dipoles in a gas do when you apply an electric field. You see that You have gas molecules, and they're all randomly oriented, of course, and then you apply a field, and of course, a dipole sort of starts to twist in the direction of the field, but there's randomness because of thermal motion, and how that balance takes place is what he described in great elegance. And then in 5 minutes at the end, said that if you took a polymer chain and you didn't stretch it, it would be all random. And then you stretch it, you get the exact same distribution function that Debye got for the dipoles, and it does a Langevin function. And I tell you, this is how I teach polymer physics today. Okay, so it really is a privilege to hear the Birnboim family. I had no idea I would ever have any connection with this lecture, aside from the fact that steal is the word that comes to mind, but that's not what it is. I'm honoring his the legacy that we are here to describe, and hopefully, especially for the students, right? You come to school, you learn something. You don't know where the journey takes you. I graduated in '88, and hopefully you'll see where the journey has taken me about the whole idea of taking polymer chains and making them move around. Yeah. So I'm going to tell you about the movement of neutral molecules under electric fields. And this work is motivated by my interest in rechargeable batteries. The work was done, actually, also UC Berkeley. You can tell that these were slides made last night. But David Hallett and Xiaopu Wang, Zach, Jiayang, all students. Narration Eugene, our scientist at Oak Ridge National Lab. Jeff Reimer is an NMR spectroscopist, and I'll talk about his work. And we work with theorist Rui Wong, who's an assistant professor, which I hope we tenure him because he changed my life, actually, after he came to Berkeley. So I'll tell you about 4 things, beginning with an introduction to polymer electrolytes and ion transport, and then going on to topics related to that. Okay. So energy contained in batteries is very much something that is on everyone's mind, especially in the context of electric vehicles. And lithium-ion batteries, how much energy you carry per liter is what the y-axis is, and the date, x-axis. So in 1990s, when the battery was invented, it carried about 200 watt-hours per liter, and you can see as time progresses, the range of lithium batteries' energies changes depending on the application. And it's a beautiful thing to have articles where all this is documented, because you otherwise hear all sorts of nonsense in this field about rechargeable batteries. And what should catch your eye is that the highest energy density rechargeable batteries essentially plateaued around 2012. Okay. So your batteries haven't gotten any better on average, at least at the high end, for the last 14 years. Okay. And to me, it's not surprising, okay? Because you all know that the batteries have an anode and a cathode, and the anode is graphite, and the cathode is a transition metal oxide. You don't change that. You will not change the energy density, okay? And so the struggle for changing the electrodes has been really at the center of going past lithium-ion batteries. And having been involved in 2 startups, I will say all startups have thus far failed. You cannot buy anything except a graphite electrode and a transition metal oxide today. Okay? One approach for enabling higher energy density batteries is using polymer electrolytes. And there's a small little company, it's not little, but there's a small company in Europe that actually commercializes batteries based on polymer electrolytes. There's another parameter that everyone cares about, which is charging time. Okay, so this is a battery. You have particles on one side, particles on the other side, and you're sending lithium ion from one side to the other. And the negative electrode will attract the lithium ion because lithium is positively charged, okay? So if I charge up and and the right side is a negative charge, negative part of your voltage. You start out with an electrolyte that contains your lithium ions. And at T equals 0, when you don't do anything, the concentration of this electrolyte is some C average, okay, moles per liter. And as you drive current, lithium ions enter from these particles, enter the electrolyte, and leave the electrolyte out here, and you get concentration gradients, okay? This is diffusion coupled with a few other things, okay? Known for a long time. If you have a current density I1 that I show here, and you get this concentration profile, you're fine. But if you increase the current density to I2, then half your battery doesn't have lithium ions. And if you increase it further, at some point, none of your other electrode is going to have lithium ions. So what limits charging rate is how these concentration profiles develop. The reason you can't charge your battery in less than half an hour is because if you try to pump more current, you'll burn up. And if there are no lithium ions on the other side, you burn up the electrolyte, by the way, because the electrons are still flowing in. So these, more or less, I'm going to be telling you about the motion of ions and neutral species in the presence of current. Okay, that's basically the subject. So my simplified view of a battery is you have planar electrodes just because it makes life convenient. You know where the lithium ions are starting, you know where they're ending, and this is a race course. Okay, you apply a charge, you expect the positive ions to go to the negative electrode, initially the negative ions to go to the positive electrodes, and the uncharged polymer to do nothing. Okay. The uncharged polymer is really a host for the ions because the ions have to come in, so it has to welcome the host. Then it has to let go of the host, of the ions, because it has to leave. And so this complex sort of solvation, desolvation dynamics that have to be done by the same material is what makes electrolyte design non-trivial. And I'm going to tell you a story of two polymers. That first is called polyethylene oxide. The bio folks know it really well as PEG. It's the same thing. It's CH2 with an O. And this company that I referred to in France actually commercializes a PEO-based battery. And I'm going to tell you about another polymer called polypentyl malonate. That's the structure there. It's got oxygens. All electrolytes that are functional have oxygens to water, for example. And those oxygens sort of help with the solvation of the cation because oxygen is negatively charged. And I will refer to concentration in terms of this molar ratio R, which is the ratio of lithiums to oxygens. Okay, you can argue about why we use that, and I'm happy to. By the way, I'm happy to answer questions while they come up, if they do. So here are some experiments that Zach and Jae-young did. You take this electrolyte in the battery, you start charging a current. At fixed current, you get a certain voltage profile as a function of hours, and you ramp up the current, and up to 0.9 milliamps per centimeter square, you get a stable voltage. You might not even call that stable, but this is what we call stable. And then you go to 1.1 and something dramatic happens. Okay, the voltage diverges. This is a standard signature of reaching what is called the limiting current. Okay, so what is happening at this between 0.9 and 1.1, let's say at 1, is that the concentration near the negative electrode is approaching 0. And when that approaches 0, in fact, it's very easy to see that, in fact, the voltage should be infinite. Because log, in the ideal case, the voltage is related to log of the concentration, and when something goes to 0, you get infinity. Okay. So this divergence is well recognized, not easy to measure, because lots of bad things happen on the way there if you're not careful about cell design, and that's really what we have done. So there's a consequence of this motion, the initial motion that leads to concentration gradients, and that's what I'm going to tell you about. And I will also show you that these are the limiting current values as a function of salt concentration for ppm and PeO. And I would argue that this polymer ppm is the best polymer electrolyte known to man. Okay. How do we know this? I don't know of any other with a higher limiting current. Okay, that's my simple measure. So most of the rest of the talk is why is this the case, right? Why are we getting so much current in this polymer? And there's an answer here which says that the molecular origin for ppm is of high, it's something called the cation transference number. And I'll explain that to you as we go along the talk. I want to switch gears. I told you a little bit about the introduction. I want to tell you about subdiffusive solvent motion and quasi-elastic neutron scattering. So this is a picture of the battery fluid you carry in your pocket, okay? Some carbonate solvents with ions, and everything in the quiescent state is moving around. And if you do a molecular dynamic simulation of the quiescent state, you actually know everything about transport. Okay. So buried in this motion of species is evidence of other characteristics of ion transport. And if you track any of those objects as a function of time, you would get that the mean square displacement goes with the time. It's proportional to time with a slope that is the diffusion coefficient. I'm not saying with the intercept that's the diffusion coefficient, because the slope is always 1. Okay. The ion might move at a different velocity. The solvent may move at a different diffusion coefficient. But in any case, that is what you expect. There are characteristic times, however, when you're shorter than that, you get subdiffusive motion. This slope is smaller than 1. It can be something we're not quite sure. But there are some characteristic times. You can say this is the time scale for a given solvent molecule to forget where it was. It has moved so far away from its original configuration that you get randomness. And I have mentioned that because of the work of people like Green and Kubo and Ansager, the relationships between the quiescent dynamics and transport are well established. So the central question, and I'm going to argue that's the central question, is how long does this solvation shell, the solvent molecules next to the cation, how long does it survive? Okay. This question was answered extremely elegantly by this group at University of Chicago and State in the context of water. And this beautiful paper showed that, in fact, when you have water surrounding ions, it lasts for about a picosecond. Okay. And this is some fancy 2D IR spectroscopy with some strange molecules, because that's what they needed. But subsequent work has shown that when you go to water, it's roughly a picosecond. Okay, so you can imagine have ion, maybe sodium, and the water molecules are in a well-defined configuration for a little while, and that little while is 1 picosecond. Okay. Not so long ago, there was this article that came up, which essentially said, using the same technique, 2D IR, I don't understand this, so if you understand 2D IR, tell me. But they said that, roughly spoken, in the liquids that you carry in your pockets, and you have been for a long time, the time scale is 1 picosecond. And then came a paper where basically they said, we don't know what it is, but that paper is wrong. That's all this JAX paper says. It's amazing. You can write a paper in JAX to say that the other person was wrong. I can't even get a paper reviewed in JAX because our stuff is so boring. Okay? But anyway, this is that no exchange takes place for at least 100 picoseconds. Okay? So they put a lower limit for the battery fluid you carry of 100 picoseconds next to the lithium ion. Okay? By the way, there was a paper by Michael Fair from Stanford like 3 months ago that showed this to be true. Okay. What I'm going to tell you about is measurement of dynamics by scattering. Okay. In fact, the picture you saw of Birnboim was he was doing a scattering experiment. You take your fluid, your ion, it's quiescent. You shine a beam. It could be X-rays or neutrons. They scatter at a certain angle, and the beam intensity would fluctuate. And it fluctuates because these things in the fluid are moving. And if you're clever, from those fluctuations, you can tell how things are moving, exactly the problem that I'm interested in. There's also another point, which is that when you come in with a beam, it's monochromatic, and so it has a fixed energy, h bar omega. Okay. And so what happens is when the beam, photons if it's light, interacts with the stuff that's moving, it exchanges a little energy. And so the scattered beam has a slightly different energy relative to the incident beam. And so you could equivalently, instead of tracking intensity, you could track the energy spread and get the same information. Okay. And this has been known for a long time. And what I'm going to tell you about is quasi-elastic neutron scattering. Like Todd said, we go to the nuclear reactor often and put in a beam and see how it spreads at certain angles. That's about it. The point is that the length scale, because of the wavelength of neutrons, is 1 to 5 angstroms. Okay, so you're actually watching on the right length scale for solvation effects. So here I want to point out one of Birnboim's legacies, which is this paper, where they looked at light scattering from a macromolecular solution, obtained the diffusion coefficient from autocorrelation from analysis of the fluctuations, that the intensity fluctuations, and they looking at ribosomal rat liver RNA. I mean, way ahead of its time. Okay, so it's remarkable that he was using quasi-elastic light scattering to measure biological molecules moving. This is how cataracts are detected today. Okay, if there's a step change in cataract detection, it's because people started doing quasi-elastic light scattering and figuring out when your proteins were aggregating. Yeah. And that happened, I think, around 2000 or so, roughly. I'm not sure. So coming back, that's all in the diffusive regime. I'm interested in the subdiffusive regime. And if you have a simple polymer, now I've taken those solvent molecules and connected them by a line. This subdiffusive regime was worked out in 1953, and it's a half. Okay, instead of a first power, you get a half power. And I'm just going to say that in honor of the man who did this, Rouse, it's an amazing story. He just published basically one paper in Science and has the whole field of polymer dynamics following what he did. I'm going to call it the Rouse parameter. I'll just to sort of help in the clarification of some processes. I'll be plotting sometimes delta R squared over T to the half. And so if we are below the segmental time, we'll get 0 for this plot. And above it, we'll get a half. Okay? And I'm going to do that in the context of these two polymers. Okay? Polyethylene oxide and the same salt with polypentyl malonate. So the polyethylene oxide work was published actually some time ago now. Sponsored by CO, by the way. This is work. They forced me to do this Quenz experiment, which I didn't know anything about. But they funded the work, and I'm very grateful for that. But this is the energy spread for one particular PEO sample at some temperature. By the way, if I don't mention the temperature, it's 90 degrees centigrade. Okay, just wanted to make that clear. You see that when you have little salt, the energy spread is large, and that's because things are moving fast. And then as you add salt, things slow down, and the energy spread is small. If you go to ppm, it's a different scale, but that's because it's a different instrument. We had to go to Oak Ridge. In fact, NIST has been shut down for 5 years, so we can't go and get that beautiful NIST resolution anymore in this country. Okay? You can take these things and get at exactly what I was talking about, which is the mean square displacement, okay, at a certain scattering vector, a certain angle. So I wanted to first tell you that the mean square displacement is in the 5 to 50 angstrom range, squared of it, angstrom squared, and the time is 0.1 to 1 nanosecond, okay? When we talk about molecular dynamics, there's a lot of talk about what the structure is, but very seldom do you get to analyze how quickly things are moving. And I don't know that there's anything else that is quite as robust as quasi-elastic neutron scattering for that purpose. All the slopes are a half. Okay? So if I had made a normalized plot, you would get the Rouse parameter plot, I would get a flat line. So this is the data from ppm, which we published last year. And you can see that the Rouse plateau, which is what I call the R equals 0, systematically goes down. And that just tells you that the friction is increasing. But there is something interesting that happens at this concentration, where you first see a decrease, a plateau, and then an increase. Okay? And I will tell you what it is. It has to do with how the ion is solvated. You see, normally when you think of solvation, all you're thinking about are what groups are involved. But in polymers, it matters how many chains are involved. And I'm showing you snapshots from Rui Wong and Xiao Fan. And they've colored the 2 ppm chains differently. Okay? So the solvation shell around the lithium ion, which is the blue dot, contains both oxygens from the anion, which is in yellow, as well as the polymer. In PEO, it's all polymer. The anion is far away. Okay? And so this, in my view, has a big impact on what's happening in the battery. So if you look, of course, this is a liquid. If you look at the solvation structures, you get a very sharp peak, the probability of 0.8 that it's one chain, and almost nothing having 2 chains or more anions. I showed you a typical snapshot from a simulation there. And this picture, if I were to draw it in a cartoon, would look like this. On the other hand, you see a plethora of 2 and 3 chain conformations with 1 or 2 anions. That's not the important point. The point is the number of chains is more than 1. And so the solvation structure looks like that. And you see, when 2 chains are stuck together, it becomes a different polymer. It becomes a cross-linked polymer. Okay? And so this new feature that I saw in the quasi-elastic neutron scattering, I argue, is because of the fact that you have a temporary network, which you never found in the case of the other electrolyte. And of course, if you do simulations are ridiculous, by the way. You can just ask any question you want, right? And so you can, first of all, get the mean square displacement. Sure, it goes down, it plateaus and goes up. you get some time constant from the mean square displacement. You can say, how does that compare to the lifetime of the sticker? And it turns out to be perfectly matching. Okay, so I'm showing you experimental data and simulations on the same time and length scales with no adjustable parameters. It's not perfect. I mean, you'll see numbers are off, but here's what it is. Okay, a good interpretation of why we are seeing what we see, and in the context of So the solvation time of lithium in ppm is 500 picoseconds. The first time any non-1 picosecond solvation time has ever been reported in the literature. Okay? The reason this is connected to ion transport is very funny. You see, when you want only the lithium ion to move, the anion, the solvent, everything else is just moving around and wasting your energy. So when this tightly bound lithium ion in PEO wants to move, it drags the chain along with it for a little while, 500 picoseconds or so, until another better crown ether-like configuration presents itself, and then it hops. Okay. In ppm, it doesn't have that constraint. And so ions just move without engaging with the polymer chain too long. So the point is, you can draw a picture like this, but there are two problems with, how am I doing on time, by the way? Yeah, all right. I'm almost there for the, this is the last real, well, yeah, nothing is important, but yeah, in what I said. But anyway, this is the last scientific little detour I'm going to take. I've shown you this picture about anions and cations moving. There's an electric field that with a gradient in the x direction. And the velocity of a species, people write in terms of a charge, a mobility, Faraday's constant times the gradient. And so if you put a charge of 0, obviously you get a velocity of 0. And I would argue that actually no one knew how to account for this motion. They understood it was important. In fact, it has been known to be important for 100 years. But the mechanics of how to do this was surprisingly absent. Here's a picture from a very good group in Germany telling you about some ion transport mechanism. This is 2022. And you see the argument here is that because the positive ion is bigger, if one positive ion leaves, then 3 negative ions take its place. Okay? I don't think this paper is right. But the point I want to make is the solvent is not even mentioned. And it's more or less true of almost all non-Balsara papers in the field. Okay. But it's just simple chemical engineering, right? If you start out with that initial configuration, if I have concentration polarization, the solvent must have moved. Right? So it's not black magic. It has to have moved. And in this case, pushed around by the ions. And in fact, if you go to this textbook, there's an equation there. Okay. The first 2 terms are nominally what you would call accumulation and convection. Not quite convection, but it is. So the first term on the right is diffusion, the simple diffusion problem. The last term is what is really interesting, which is the introduction of current. Okay, so if you have current flowing, then you are forced to take the dot product of the current times the gradient of this parameter that I call the transference number. So at this point, I have to unfortunately tell you what this is. Okay, and it is defined as the fraction of current carried by the cation that relative to the solvent velocity in an electrolyte of uniform concentration. I'm not going to belabor the point, but a lot of folks, if you want a discussion about this parameter, I'll tell you about it more. But I want to tell you first is that that annoying term, C times V0, V0 the solvent velocity, had been set to 0 through the entire history of electrochemical engineering. Okay. So this is the flux in this really, really famous paper. This is the only theoretical paper in the Nobel report. Okay? It's the way all EV batteries are designed. It has no solvent motion. Okay? And the argument, I think, might be sound, which is that, you know, when you look at this equation, it's likely that the other terms dominate. Okay? I'm here to tell you that's not true. But the first thing I had to do was to, and I'm a friend of John Newman, the author of all this. So I called him up and I said, you know, how do you, oh, sorry. How do I, you know, what do I do with this one equation? He says, you need another equation, obviously. And then COVID came along. Okay? So I started going back to my undergraduate notes. And the missing equation, John told me, would be the divergence of the velocity field. Okay? So we know that the divergence of the velocity field is 0. This is called the continuity equation. The day you understand that this means what goes in must come out is the day you become a chemical engineer. Okay? I did not become a chemical engineer when I first saw this equation. Okay? But this is actually my undergraduate notes when I first took that into my psyche. And the big question is, how does the continuity get modified if you have current flow? Okay? It turned out to be a much more difficult problem than I had envisioned. And COVID was perfect. I had nothing better to do, so I sat down and derived that equation. Okay? And so in this paper, I would argue for the first time, you could do the simple thing of accounting for the motion of neutral species. Right? Not that complicated. Yeah, I argue before 2022, no one knew how to do this. It's stupid. I mean, I'm not a good deriver, by the way, by any means, but I was able to do that. And as a consequence, there are many equations in the field that, in fact, were unknown. So, for example, if you know the transference number T plus 0, the solvent velocity is fixed. V bar turns out to be the partial molar volume of the solid. Okay. So folks, it's very simple, right? If you have a cation and anion, and the field makes it move, and the volumes are not identical, the solvent has to do something. The solvent rearrangement has been around for a long time, and even something simple like this has not been in the literature. V0 has been assumed to be 0 when T plus 0 is not 1. When the transference number is 1, it means only the cation moves, and there you're all golden. But if the cation and the anion moves, the solvent has to move. And in hindsight, this is not rocket science. Okay. And so, in fact, we have papers where we perversely just measure the solvent velocity and give the transference number, which is the fraction of the current carried by the charged species, with no problem, right? Well, as we were doing all this, we started measuring the transference number of this PEO. And this was a paper that was caught people's attention. I mean, this work. First of all, it's very hard to measure by classical electrochemical means. I make no excuse for this. This is probably the best measurement ever made on any electrolyte, but it has error bars that are presented for real. The best we can tell, the transference number at R equals 0.14 or so is negative. Okay. And now the negative current drives everyone crazy. In fact, I was given all sorts of lectures on electrostatics on how this can't possibly be right, especially in a polymer that everyone has studied since the 70s, right? The point is that, of course, it's hard to measure. And not surprisingly, it generated some controversy. You know, your name comes in the abstract, and then it says that you're completely wrong, right? we confirm the literature and not this crazy. They talk about the Newman approach, but it's really the Balsara approach because Newman was, of course, always there, but the measurements and all the, so I take responsibility. I felt very bad that Newman got his name in an article that was so negative about everything we did, right? The whole objective of this article was to show everything we did was wrong. And of course, it violated everything else in the literature, right? But there were other people who actually took it seriously. And this was a simulation from MIT where they finally apply our method to a realistic case. This is our data. And they had an explanation. And the explanation is what exactly a lot of people think when they think of negative transference numbers, and they appreciate that it can be negative. The idea is that the ions are clustered, and that there are enough ions, positive ions, clustered with negative charge moving in the wrong direction, which is what gives you this net flux of both cations and anions to the same electrode. Yes? We don't, I don't know. I mean, nobody, this is what we have elucidated in great boring detail. But yes, it has to do something. Yeah. So we set about measuring these velocities, and this is where Jeff Reimer comes in, using electrophoretic NMR. So you take an NMR tube, you fill it with your electrolyte, you apply a field, and we can't do polymers because you can't stuff a polymer easily into the tube without breaking it and put the electrode. So we are going to show it to you on a simpler case. The solvent has protons, salt has lithium, the anion is fluorine, so you can track all three species, and you apply the field. This is an oligomer of 4 ethylene oxides, and we measured the 3 different velocities as a function of molarity. And it turns out that, and these are not trivial measurements. Each of those data points is based on several measurements of NMR measurements. And then in this paper, we finally sort of use these measurements to get the transference number. And a cleanest definition of the transference number is that if you get the field-induced initial velocities, it is just this ratio. Okay. You see, and here's the point. In fact, Steve made a very, very important point. You're talking of a velocity. When you speak of a velocity, you have to ask the question, what is the reference frame? And the implicit answer, when you don't know it, it's actually the solvent. Okay? And so, in fact, you're sitting on the solvent and looking at all this, and you don't know that you're sitting on the solvent. Very often, you don't know what your reference frame is if you're not careful, right? And so that has been one of the problems with all of these methods. And so, in fact, when you make all these, do the Ansager analysis, and I don't want to belabor the point, you analyze the quiescent simulations, you see exactly that the transference number of ppm is higher than that of PEO, mainly because the solvent is not being dragged by the cation. The cation solvent correlations are diminished. It's actually not even easy to see it in the Ansager coefficients, because the Ansager coefficients that are relevant are the ion-ion correlations. The solvent is hidden. So you have to go one layer deeper to understand the origin of why these transference numbers are different. You can just see that the correlations are completely different in the 2 polymers. The last bit of the puzzle I want to say is that now I have a student, Emily Abdo, and she can do this thing. This is the concentration as she's polarizing, okay, using X-ray imaging. It's sort of crazy, right? I mean, you take the cell, you go to a synchrotron, you take a measurement. The salt scatters X-rays like crazy. The polymer doesn't. So wherever there's high scattering, you have high salt concentration. And this is quantitative because the scattering cross-sections are all known. So there's no approximation. And so you can sit, for example, in the middle of the cell and see how the concentration evolves as a function of time. And then use simple chemical engineering, where velocity is the only unknown if you know how this concentration is evolving with time. And so we are now at the point where we are getting solvent velocities as a function of space and time. And you can see it's not quite flat, but we expect it to be flat. And that's the V0 we will put in when we figure all this stuff out. Yeah. So I want to finish by coming back to solid state batteries. We're done with all the thinking, by the way, if you're tired. So this is what I started out with, the idea that your energy is constrained by the electrodes, and you need another kind of electrolyte. And then this paper came out. Okay? It rocked the boat. In this paper was a beautiful plot of different electrolytes. Our favorite polymer electrolyte is here. This is the liquid electrolyte you carry in your pocket. This is the one they proposed. Okay. And of course, the world will say, you look at this plot and say, which one do you like? Do you like this soft, compliant, lousy electrolyte that Balsara works on and had nothing to do with as far as invention or anything? Or would you like this hard electrolyte that has amazing conductivity? Right? The whole world has jumped on the obvious answer. And since 2012, lots of announcements have been made about solid batteries. Here's an announcement that is more recent, 2022. They said the first vehicles for solid-state batteries will go in 2025. Toyota is the company that is in cahoots with that Japanese group. Okay? I couldn't believe that this even exists, but there are publicly traded battery startups. How that happens is a miracle of finance. But you can buy stock in solid-state batteries. You can't buy a solid-state battery, but you can buy stock in it if you want. Okay. And I have a simple answer of why this will never work, which is why I've always worked in the soft electrolyte field. You see, imagine two sets of particles separated by a solid, right? A hard glass-like solid, and it looks perfect. There's a problem because batteries, particles, the volume has to change when lithium goes in and out. There are many solids in which, by the way, when lithium comes out, it actually expands. Because, in fact, when it goes in, it's a charge and it brings the framework together. So the sign is not important. There's going to be one problem at some electrode. Okay. And if you have a 1 nanometer gap in a 1 micron size particle, you can calculate what the volume change is. That's an insulator. So these electrodes, in my view, a hard solid electrolyte, in spite of the conductivity, will never work. And so you need something that's like chewing gum that can follow the receding particles. This is not easy to do, trust me. I've been working on engineering these kinds of things in startups with the most amazing teams and with 50 people working on this, and it's not trivial. But that's essentially, in my view, the problem with solid-state batteries that remains to be solved. What do you do about the battery electrodes breathing? All right, so neutral molecules must move when you apply an electric field. The formulas are simple. This is not rocket science, right? I'm very proud of developing a continuity equation. I barely understood it, but the fact that I was able to derive it and by the way, if COVID doesn't happen, this thing would never have happened because I had this objective for a long, long time. And finally, when I realized all the things I had to learn to get to that final answer, it was not going to happen in my lifetime. Okay, someone else would have done it. The movement of neutral molecules is not something to be, just for theory. I mean, high transference in our favorite polymer, PPM, is exactly because of that, because the neutral molecules don't move as much. And my feeling is that all solid batteries will not happen without a soft ion conductor to allow this battery to breathe. I want to bring back the notion, again, to me being a student here, learning from you folks, and then going out in the world and doing something, and these are the students who did the work that I described so proudly, right? Saheli, Zach, Xiaopang, Jayan, Neil, and it's because of you guys that we have so much fun. Thank you very much.
Thank you, Nitash. That was wonderful. Some questions, and suggest that perhaps students can come forward with questions first.
So one of the reasons why people advocate for hard solid electrolytes would be to kind of suppress dendrite formation, which might be an issue if you use soft solid electrolytes, because your dendrites might actually penetrate and make it to the other side. So how do you, defend that?
This is a very, you're obviously extremely knowledgeable.
Thank you.
So I did not allude to the fact that one of the target electrodes is lithium metal, and that one of the problems with cycling lithium metal is that you grow dendritic structures from the surface of lithium metal, and that solids are needed to suppress that. Liquids don't. Whether or not a polymer has the appropriate modulus, it turns out to be a modulus problem, and we have I want to say about 50 papers on the subject of dendrite suppression in polymers. Of course, the harder the solid, the better the dendrite suppression. There's no doubt about that. And so we cannot, with sort of megapascal-ish polymers, compete with a gigapascal solid electrolyte. But whether or not it's enough, I don't know. CO, my first company, was working on block copolymer electrolytes that had a high modulus to suppress dendrite formation. We are working with silicon as an anode to avoid that problem altogether. So it's a very important question. There's a history, and I can talk to you about dendrite in fact, when you have a polymer and a block copolymer, you don't get dendrites, you get what are called globules, it turns out. So there's a whole other, it's a beautiful subject, and I'm amazed that, I'm not amazed, I mean, it's an amazing question. Yeah, an amazing student, yeah.
Any other questions from students?
You have a question? No?
No? All right. Professor Belfort?
Yeah.
So first of all, I want to say that it was a wonderful book. I love to see how you explained a very complicated world without many equations, which I love. But so I have actually 3 questions. The first one is, I always understood when you increased the current density, you would eventually reach a point at which you induce vortices at the surface. Remember that work by Ruckenstein and work done at Princeton also by, I forget his name, but it was a beautiful. So what you do is you get a lot of, suddenly the current goes up and the thing goes crazy because you get vortices bringing in new material to the surface. So that's question 1. The other one is the solvent must move is the same as what we study with particles. If particles go from A to B, solvent must go from B back to A. So there's a solvent movement always when particles move. So if you induce this to occur, like your particles are moving along, your ions plus polymer, then you must have solvent going in the other direction. Or it could be carried with it, depending on the hydrogen bond. The third question has to do with measuring hydrogen bonds in your system. We've just done it with solvation cell spectroscopy. I wondered if you've ever used that method to see what the hydrogen bonds are around. And I have other ones I'll talk to you this afternoon about.
So, we have not done, working backwards because of my short memory, we haven't done any spectroscopy, so I look forward to learning about that. I agree with you. In fact, it's no mystery that the solvent moves. Okay?
It has to move.
It's just that there weren't any equation. No one could tell me what to do about it except wave my hands. And your first question about vortices, I'm unaware of that literature, but perhaps by using polymers, which are high viscosity materials, we avoid those kinds of instabilities.
Right, I think so.
And so we can use the simplest versions of the velocity field. And so that we might have done. I know for a fact that using polymers has allowed us to dodge a lot of electrochemical bullets. Yeah.
Good, thank you.
Professor Garai?
Hi, Nitash. Really enjoyed your talk. And I'll start with the disclaimer that I work on solid-state batteries, the hard-solid electrolytes. So I feel a need to defend it a bit. I want to just follow up on that other question that we use solid electrolytes to suppress dendrite formation. But there are additional benefits, which is interfacial stability. So I'm curious about how does the polymer play out? Do you get better interfacial stability with high voltage cathodes, with lithium anodes? And the second question is, what about long-term degradation of these polymers? Is that an issue?
Now, these are all really, really good questions. I think that interfacial stability is something I didn't talk about. And long-term cyclability, I didn't talk about at all. As you know, both these things are measured very badly in our field. Okay, I mean, there are old papers that say that if you use a planar anode, that's the worst way to measure interfacial interfacial growth. You need particles, right? You need a lot of surface area, and invariably you find a cell with a planar lithium electrode claiming 5-volt stability. I don't know necessarily that polymers are less stable against lithium, and I look forward to an apples-to-apples comparison between inorganic solids, and solid polymers. I don't think it's a showstopper. That's where I'll put it, right? Yeah. Did I answer your question?
Yeah, sort of. Yeah, thank you.
Professor Kramer and then Professor Zoff.
Okay, thanks. Nitash, what a pleasure to see this talk and to see how much amazing stuff you've done really recently. So it's super cool, right? I have just a question about why does your PPMA, whatever the polymer, why does it do the sort of solvation and then letting go as compared to the PEO? What is the molecular basis of that? Is it a polymer structure thing? Is it a moiety interaction thing?
You can tell I shouldn't be doing much of anything, but it is purely a polymer structure thing.
That's what I figured, yeah.
The point being, if I can ever find both of those structures. This is horrible. The beautiful thing about polyethylene oxide has always been that it has this crown ether-like structure. Okay, that 4 or 6 of them can go around and do the solvation thing. Okay? That's the Achilles heel. There is no such motif in the structure of ppm. It has these 2 oxygens sitting right next to the carbon, which are horribly placed for solvating, and this other oxygen actually does nothing. It doesn't participate in solvation. Okay, and so because one molecule doesn't have the right motifs, it gangs 2 or 3 of them. It's not that complicated. In the simulation, just never happens with one, right? I mean, that's the beauty of, you cannot, you can see 1 ppm chain, it's like yellow, right? It's all 0. And then there's no configurations that.
So quick follow-up.
Yeah.
Better? Sorry. Quick
What?
follow-up. Is there any opportunity to make an even better polymer?
100%. I mean, for sure. I mean, we just hope that, I have seen AI-based approaches to make polymers better. They don't have any solvent motion in there. Okay. And I would argue that there's nothing yet better than PEO because of that. And I think I still have hope that thinking through problems in a non-AI way has some value.
Professor Zah, and then Professor Belfort.
Thanks, Nitesh. I have probably a really naive question. When I look at your ppm and PEO chemical structures, they don't look liquid to me. Are they really low molecular weight? We're essentially in the melt, right? There's no other solvent.
That's a good question. So PEO, as you know, is crystalline at room temperature.
Right.
So that's why we choose 90 degrees centigrade, by the way, to get away from it. ppm is completely amorphous. The glass transition of ppm and PEO is -50. Both are very similar. Yeah. So these are liquid polymers, and we use 30,000 molecular weight grams per mole, roughly, when the properties are independent of chain length.
Mm-hmm.
Okay.
But there's definitely temperature dependence. Like if these batteries get too cold,
Absolutely.
they really change.
Yes. So it's a very interesting question, right? It turns out that the electric vehicles carry 2 refrigerators with them to keep the battery temperature below 35 degrees centigrade. Operating a battery at 60 degrees C is no problem whatsoever. Okay? And so, in fact, one of the things that CO did, it was eventually bought by Bosch, which is a car, they built packs. Their packs were simpler because it needed heat and not cooling. And of course, we have lousy electrolytes, so the I²R heating is also a lot. But so it wasn't hard to manage those batteries. And so as long as you're not, if I had to relive my life, I would start at a different temperature, not 90. But we just started, in I don't know, 2007, we said, what temperature should we run the lab at? And we said 90, not thinking that it would be, it certainly works at 80, and then at 70, it's a little more sluggish. So I think that whether or not, it can't work on your cell phone, but on the EV side, it actually may be beneficial to have it slightly above room temperature. So that, I mean, you hear of all these things, right? You put an EV in the hot sun in Arizona, and it has to cool while it's in the parking lot. Because otherwise, once the battery temperature reaches 65 degrees, it can't be used again ever. Mm-hmm. And the 65 degrees is very easy to get in the sun inside a car. So.
Great, thanks.
Professor Belfort. Other questions? Here we go. Students?
I have a question in the molecular side. When you apply this electric field, right, what is the force or like the pull felt on like the lithium ion, because lithium ion is in the electric field, it's going somewhere. How much pull it is getting on the polymer? And do you think there is like a chain of this oxygens that are, spread around, like the lithium can jump and go around?
So those are all the things that we have worked out in excruciating details in our papers, right? I mean, what matters, by the way, is the distribution of lifetimes of these polymer ion complexes. And the nice thing is that what I've shown you is actually some experimental data validating some of those lifetimes. Okay. But from that angstrom length scale to continuum, we have it all covered in publications, right? And so far we see just consistency, mainly folks, because the founders of electrochemistry were geniuses. These guys are amazing. They just knew everything. We just have to follow what they're doing. Yeah.
All right, we'll have a student question and we'll have our dean wrap things up for us.
Thank you for the talk. I had a question comparing your quiescent measurements and what would actually happen in a battery. So in quiescent measurements, if there's a correlation between the polymer and the ion versus when you have an electric field, since there are like polar groups on the polymer, could it like orient in some direction, and how would it affect your polymer and ion correlations?
So, so far, there are many ways to get parameters, transport parameters. Some of them analyze quiescent data. Some of them actually have analyzed, you apply an electric field in a box and you simulate and you get a net velocity that's not zero in the direction you expect. All those answers are identical, right? It's only a matter of sampling and which one is more efficient. And my understanding, not being a simulator, is that the quiescent simulations are the best way to sample what you need, provided there are no, you don't need umbrella sampling and you're not getting stuck in some bottlenecks and things like that. So my understanding, and this was Ansaga's hypothesis that has been proven again and again, and once in a while it's disproven again to know that this person was wrong. So I feel like what Ansaga said has held out so far to the extent that I can see. It's a good question.
Thank you.
All right, a final question from Dean Garde.
Nitash, two quick comments. One is echoing Steve. It's fabulous to have a distinguished alum like you to come back and we get to learn from you. It's also wonderful to see molecular simulations being useful somewhere. So two quick questions. One is for solid state battery people, should they be looking for a breathing agent that doesn't interfere, but its job is to simply occupy volume when it's created?
Can you repeat that?
For solid state battery,
yeah.
Should they be looking for this kind of a not liquid but moving breathing agent, whose job is to not interfere but to simply occupy volume when it's created?
Yep.
And the second question is, should we be thinking about cathodes in your first example where microstructure is actually different from left to right so that all of it is accessible at high currents or high power, let's say? Yeah.
So those are true questions. The first is that this flexible electrolyte, you don't need it to be occupying the entire battery, right? And that's to your point, right? I mean, it could be that there's a composite. There's a question about composites, whether the ion actually ever hops from one phase to the other. That is still an open question. Yeah. Lots of people, I think, well, I'll just say it, okay? I think up to about 2 years ago, everyone thought that a pure solid would do the job. And there are an increasing number of my friends who believe that not to be true anymore. So they increasingly come to me to talk about composites. And now we have a fair number of DOE programs on composites. The idea being perhaps that, the way I like to see it is you want to get from one side of one shore to the other, and you have a fast boat that stops just short of the final destination, and a slow boat that takes you all the way there. Obviously, some combination of boats may be better, and that's so I think that that's the answer. And the idea of structuring the electrode to facilitate full charging is a very important one. The way electrodes are made is ridiculous, right? I mean, it's by slurry casting, and somehow they're all electronically conducted. I mean, it's magic, but there's a lot of room to think about engineering that to facilitate charging. That's a geometric problem that I believe can be solved, and perhaps people will solve it. Yeah, it's a good question.
Thank you very much.
Thank you.
I have 3 levels of thanks to distribute. First of all, I want to recognize the AV staff and the office staff, in particular Lindsay Cronmiller, for organizing and pulling the events of the day together. Thank you very much. The AV went off beautifully. Thank you very much. I would like to thank the Birnboim family again for making this lectureship possible and for allowing us to bring back such wonderful speakers like Nitash, Balsara, and honoring the memory of Professor Birnboim. Thank you very much again. And again, Nitash, thank you. That was wonderful. Really, truly wonderful.
Thank you.
Enjoy the day.